Okay, great. As you know, I'm Elnaz Seylabi. I'm an assistant professor at the University of Nevada, Reno. And in this presentation, I want to talk about our ongoing effort to kind of model three-dimensional shallow crust nonlinearity in broadband deterministic earthquake simulations. And this work is, of course, by close collaboration with Dominique Asimaki from Caltech and Dorian Restrepo and Ricardo Taborda from EOFET University. Okay, so I mean, as we other speakers discussed in the morning, in order to do deterministic earthquake simulations, of course, we need different ingredients. We need to define the source model. We need to define the velocity structure in the computational domain. In many cases, of course, this is a multi-scale model. And also we need to have a platform to solve the wave equations. And thanks to the advances in high performance computing, now we can perform broadband deterministic earthquake simulations and push it to very high frequencies, which is in relevance to most of our civil infrastructure and buildings ranging from tall buildings to steep structures. And this means that now, basically today, we also need to be concerned more than before about our near surface geometrical and the way we model them in deterministic earthquake simulations. Because as we increase the frequency of these simulations, these layers can be seen better by the incoming waves. And of course, when we increase the level of the shaking, these near surface geometrical are susceptible to behave nonlinearly. And some of the primary effects of nonlinearity are the reduction in shear modulus, an increase in energy dissipation in terms of material damping, and some consequences could be the reduction that we see in site amplification factors and increase in residual deformations. And today we can think of different proxies to model shallow crust nonlinearity at the regional scale. So I would say that one widely used approach is the hybrid methodology, where we can perform three-dimensional earthquake simulations. It can be elastic, and then we can use the output of that to perform site response analysis. In many cases, we do the one-dimensional site response analysis. And for that step, of course, we can use very advanced constitutive models. But by using this hybrid methodology, we're kind of putting aside the three-dimensional nonlinear scattering effects and considering the simultaneous effects of source, path, and site. There were some studies to kind of try to approximate nonlinearity in three-dimensional simulations by extending the concept of equivalent linear analysis. But although that methodology can be useful in a small stress that we don't have that much nonlinearity, but it is in general incapable of modeling residual deformations. So it seems that the most rigorous approach to consider nonlinearity is basically to perform three-dimensional nonlinear analysis. And depending on the accuracy of the constitutive models we use at this step, we are able to model both residual deformations and three-dimensional nonlinear scattering effects. But as we kind of increasing or enhancing these models, of course, we can increase the computational cost significantly. As you know, today we have a rich library of constitutive models for geotechnical and earthquake engineering applications. Here I'm showing a list of models reviewed by Lade in 2005. Of course, this is not a very complete list, and we have other models as well, but it gives some a sense of the complexity of the models we have today. It can range from very simple elastic perfect plasticity model to very advanced critical state models. And in some cases, when we add complexity to these constitutive relations, we can increase the number of the phi parameters significantly, and we can have, let's say, 10 to 15 parameters that needs to be calibrated to be used in our analysis. So the question is that which of these models are suitable for regional scale simulations? Of course, I mean, we cannot start with very complex model because it would be impossible to calibrate them at the regional scale. So researchers started to look into this problem by using very simple models, and the first try was kind of elastic, perfectly plastic models. And as I'm trying to show here, we know that by using this model, we don't have any hardening. And therefore, this model can barely capture the shear modulus reduction curve, which is one of the main features we want to have in our constitutive models for near surface geomaterial. So disadvantage for this model are in general their incapability to reproduce the behavior of most geomaterials. In many cases, they can result in artificially large hysteresis loop at large strains, and therefore due the overestimation of residual deformations and attenuation. And also for a small to moderate range strains, they are basically blind to the effects of nonlinearity, as they're just capturing the maximum shear modulus. So it means that if we really want to move toward considering shallow crust nonlinearity at the regional scale, we need to use more rigorous models. And it would be important to go beyond perfect plasticity. But we need to have some considerations here. First of all, we want to make sure that that model is still computational efficient. So probably we don't want to start with a model with, let's say, 10 to 15 parameters. And at the same time, we also want to make sure that these models can be calibrated with a minimum amount of information at that scale. So considering these two factors, Southern California Earthquake Center started supporting the efforts of incorporating relatively simple but rigorous models in two of high frequency deterministic ground motion simulation software packages. AWPODC is a finite difference code developed by Kim Olsen and his team at SDSU, and they try to incorporate a model which is basically a stack of elastic, perfectly plastic models connected to each other in parallel. And by that, they can kind of introduce soil hardening into their constitutive relation. And Hercules is an octree-based finite element code developed originally by Jacobo Bielak's team at Carnegie Mellon. And there we tried to incorporate a bounding surface plasticity model. And when we take a look at the performance of these two models in capturing the shear modulus reduction curve, we see that both of them are doing way better job compared to the elastic perfectly plastic model. And basically both of them having a few number of the parameters that can be calibrated or determined by having the G over G max curve and also by having the soil strengths. So I just want to talk a little bit more about the model we have implemented and kind of verified in Hercules. So we did, in order to make sure that the model is working well, we did verifications at different scales. Here I'm showing the results for material points and also analysis and also for a site response analysis. For both cases, we compared the results against a similar implementation of the same model in OpenSys. It was actually by Gang Wang, who is going to present in our next session. And as you see, the model is working really good in comparison to our reference solution. We also tested the model in three-dimensional problems. Here I'm showing a cube of size of the edge size equal to 128 meter. We define a two-layered basin inside the model that can go nonlinear. We define a point source as a double couple. And then here is the results of the stress strain tensor at different depths. We're comparing our results against, again, OpenSys that have the similar implementation. Of course, here we are not getting perfect agreement. And this is kind of reasonable because, first of all, the models are implemented by completely two different teams. So it's not the same implementation. And also we are using different time integration methods in Hercules compared to OpenSys. So after building confidence and feeling comfortable with that implementation, we moved toward using this model for performing deterministic ground motion simulations. For that, for now, we're considering Garner Valley as our test bed. And this is the valley in Southern California. It is between two fault zones. One is San Andreas and the other one San Jacinto zone, San Jacinto fault zone. And today we have, different magnitude earthquakes recorded there. The largest one within the 50 kilometer from the Garner Valley downhole area is about 5.4. And this is one of the well-instrumented sites as well. It's used a lot for verification and validation purposes in site response analysis and also solid structure interaction problems. So at the beginning, we decided to kind of put the source effect aside. So we did plane wave simulations. We considered vertically propagating shear waves that are kind of polarized along the small edge of the model. Also, we wanted to see what is the effects of frequency content of the excitations. So we defined two input motion. One is low frequency, which is the recurve wavelet with a central frequency of 1 Hertz. And the other one is the high frequency input with a central frequency of 3 Hertz. And this figure on the right shows the depths to the shear wave velocity of 800 meters per second. And for defining the velocity structure within the computational model, we use the scale velocity model with the optional LE geotechnical layer. So here you see that basically two values. One is the one that a Garner Valley downhole area is located, and we have another valley next to that. And the depths of the both of the valleys are kind of shallow. They're going to be about 90 meters in the deepest part to reach the shear wave velocity of 800 meters per second. So here I'm just showing you the spatial variation of the peak ground acceleration. And for both cases, we are normalizing that to the outcrop PGA. And we made sure that for basically both low and high frequency excitations, we have the same PGA. So they're kind of normalized with the same number. So you see that for the low frequency case, of course, the effects of near surface layers are not that significant. Therefore, when we go from linear analysis to nonlinear, we don't see that much change. But when we consider the high frequency excitations, now you see that in the deepest parts of two valleys, we have a significant reduction in PGA compared to the linear analysis. At the same time, as I mentioned in my previous slides, one widely used approach is the hybrid methodology, that one uses the output of linear, three-dimensional linear analysis to perform one-dimensional site response analysis. And we did the same thing here. Basically, we defined around 3,600 stations over the region. For each, we did the one-dimensional site response analysis, both linear and nonlinear. And here is a comparison to the case that we do the fully three-dimensional simulations. So let's focus on the high frequency part. As you see here, in contrary to the three-dimensional case, when we make the soil nonlinear, then we don't see those reductions anymore. And that is kind of reasonable because for the three-dimensional case, of course, we have the attenuations which are based on the three-dimensional effects, and we're kind of putting that aside in our hybrid approach. So these results suggest that using hybrid methodology might be, in some cases, misleading. And then we decided also to perform the earthquake simulation, so basically bringing the source effects into the picture. For that, we're modeling a relatively, moderate level earthquake in Garner Valley region. That is the 2010 5.4 Borrego spring earthquake. Here I'm showing the slip function for that kinematic source model. And the size of the model for this one is about 65 by 65 kilometer and the depth of 30 kilometer. So just to give you a sense of the time of calculation, we have about 500 million elements. For the nonlinear case, we had about 20% of our elements to go nonlinear, and we set the maximum frequency to be 3 Hz and the minimum shear wave velocity to be 250 meters per second. And when you take a look at the runtime, you see that for the nonlinear case, the time was about 14 times of our linear analysis. And for that, we use basically a Stampede supercomputer. So here is a kind of two movies to show the variation of peak ground displacement by time for both linear and nonlinear simulations. And as you see, of course, this is a moderate scale earthquake, but still we see the residual deformations kind of increasing and creating in our two valley structure and soft sedimentary soil. And when we compare the peak ground displacement and peak ground acceleration, we see that for displacement, of course, we see an increase when we do the nonlinear simulation. But for the peak ground acceleration, we have a good amount of reduction in basically in our values. And the only exceptions are at the valley edge that we have the complex probably wave interference there. So, these results so far are just suggesting that by considering nonlinear simulations and the resulting three-dimensional differential ground motions and the shift that we can have in predominant frequencies, the seismic risk to both distributed lifelines and buildings can change. And these are some things that we need to consider in our deterministic earthquake simulations. But of course, we are at the beginning, and there are lots of gaps that needs to be filled in the future. And I just want to emphasize again that today the accuracy of our deterministic earthquake simulations is limited to our knowledge of the elastic and inelastic plastic behavior of Earth's material, specifically the shallow crust. So in future, we really need to focus on that part as we push to higher frequency and when we want to study the effects on our civil infrastructure. And also we need to make sure that we kind of enhance our simulation software packages to be able to perform scalable nonlinear simulations. So far, we are doing great in linear analysis, but we don't have such scalable packages for nonlinear analysis. And in addition to that, of course, we need to enrich the library of the constraint models that we can use at the regional scale. We need to enrich the existing velocity models to incorporate the constraint model information and also the water table information when we want to study the pore water pressure variation. And another important thing is having a validation of these three-dimensional linear and nonlinear simulations at the large scale. Of course, we spent decades to kind of validate our nonlinear site response analysis, but now it's the time to do it at the larger scale. And after building confidence on our simulations, then we need to revisit the predictive capability of the hybrid proxies we use today to kind of add or superimpose linear and nonlinear site effects in our ground motion models. And at the end, I believe that we need to enhance the modeling capabilities to use the outcome of our nonlinear simulations in engineering applications and of course in connection with large deformation problems. So I want to stop here and I want to acknowledge SCEC for supporting this research, TAC and Blue Water, so that allowed us to perform all these simulations. Jorge Crampian from Chile helped us with the kinematic source model generation, and that help is really appreciated. And we always had lots of questions in generating E3s from stake velocity models, and Philip Mitchell and Mayhu Su helped us a lot. And with this, I want to thank you for your attention.